All right, so today we're looking at lesson 47. We're looking at Kirchhoff's laws. And if you Google how to pronounce that, you're going to come up with a couple of different ways to pronounce it. So anyway, we'll do the best we can. Kirchhoff's laws. That's what we're going to be looking at today. Hopefully you'll understand his laws after this lesson. Gustav Robert Kirchhoff, from 1824 to 1887, was a German physicist who made contributions in spectrum analysis, optics, and electricity. So all of those areas is where he did research and made contributions. Two rules of electric circuits are named for him and are called Kirchhoff's current law and Kirchhoff's voltage law. So he's got two different laws or rules dealing with electric circuits. These rules provide a foundation for the analysis of electric circuits. The current law says that the same amount of charge must enter a junction in a given time frame as the amount of charge that leaves the junction in the same time frame. Okay, so same amount of charge must enter in the same time frame in a given time frame as what leaves in the same time frame. So the book says that his current law is just a common sense rule. And they say what comes in must go out. So if you look here, we have 5 amps that are going in, and on this one we have 1 that is going out. So this I sub 3, that means that 4 have to be going out on it. That would have to be a 4 because if we have 5 coming in, we've got to have 5 leaving. So we have 1 here, so we have to have another one there. So it says what goes in must go out. So it says that this version of his current law is seldom used or seldom encountered. The versions that are encountered often make this rule difficult to understand. And so I'm going to draw you another picture to go, not this one, to go with this algebraic sum of the currents that enter a junction must equal 0. So the algebraic sum of your currents that enter your junction must equal 0. So if you look at what I'm about to do, we're going to have 1 going this way, and then we're going to have 1 going this way, and then 1 going this way. And so if this is I1, I sub 1, and this is I sub 2, and this is I sub 3. We know that I1 plus I2 plus I3 has to be a 0. Okay, so they have to add up to a 0 because the currents that enter the junction must equal 0. So if we have a picture that is similar to this one where we have 5 amps going this way, and then we have 1 going up here, and instead of going out, we have 1 more that's coming in this way, and we want to solve for I3. We know that 5 and then minus 1 plus I3 equals 0. And they did a minus 1 to make it come towards the direction. It's a 1 leaving, so it's a negative 1 going the other direction. And so I sub 3 is going to be a negative 4. And it's a negative 4 because it's coming in this way. When we did it on the last slide, the last part, it was going out, and so that was why it was a positive 4. But since it's going in this way, it's a negative 4. Okay? And then we've got one more. The algebraic sum of the currents that leave a junction is 0. So this is another way that they can state it. The algebraic sum of the currents that leave a junction has to be 0. So if we have I1 going this way, I2 going this way, and I3 going this way, those all 3 add up to 0. And so now we're looking at this picture. We're going to change the 5 and make it go out. And so that would be a negative 5 because it was 5 going into it. So now going out of it, it's a negative. And then plus the 1 and plus the I sub 3, and that's going to be equal to 0. And so that means that I sub 3 equals a 4. And so that is his current law. That's just different ways to deal with it. So we're going to look at an example. We want to find I sub 1. So the point where 3 or more wires connect is called a node. So we've got a node here, and we also have a node here. And we decide to sum the currents that are leaving node B. So we are going to be looking here. And we know that all of them that are leaving have to equal a 0. And so since they're all going out, we can say I sub 1 plus 5 plus 3 has to equal 0. Because if they're all leaving, they have to equal 0. So that means that I sub 1 equals a negative 8. And so that would be your answer there. We didn't choose the wrong direction for I sub 1. It just, because of the way the arrow is, it just happens to have a negative value. So that's just based on the arrow that they provided with us, that's why it's a negative value. Okay? Looking at this one, we want to again find I sub 1. So on this one, we have points A, B, and C are 30 volts higher than points D, E, and F. And so the potential at B is going to be 30 volts higher than the potential at E. And so we need to find I sub 2 first. The way we're going to find I sub 2 we're going to use our formula V equals IR, but instead of just solving for I, we're actually looking for I sub 2R. And so we know our voltage is 30. That's what they give us here. And our R is a 10, because that's what's right there. So our I sub 2 is a 3. And so the potential at C is 30 volts higher than at F. And so we know that the voltage for C is 30. We don't know I sub 3. And then we know that our R is a 5. So that's a 3 here. And so your I sub 3 is a 6. And so now that we have our I sub 3 and our I sub 2, we can solve for our I sub 1. And so our I sub 2 is going this direction. Our I sub 3 is coming around this direction. And this is a 3, and this is a 6, and then this I sub 1 is going that way. So we need to have, we have 3 and 6 coming in. We have 9 total coming in. So the amount that is going out has to be the same. And so the I sub 1 has to be 9 amps. And so that would be your answer there. Okay, so now we're going to look at Kirchhoff's voltage law. And it says that it's just as easy to understand as Kirchhoff's current law. And so it says to consider the following elevation problem. And I think the way that they explain this is kind of funny. They use a picture, and I didn't make the name up. It's John. John stands under the tree. You see John right here? There's a little man standing right here. So he's standing under a tree. Then he climbs to the top of the house, which is 20 feet high. So he's climbed up 20 feet. After that, he decides to jump down a distance of 28 feet into a hole. And miraculously, he does not break anything. Please do not go jump 28 feet off of a house into a hole, because you will break something. And then you're going to blame it on your physics book because they had someone jump down a hole and they didn't hurt themselves. Don't do it. So we've got him jumping down into a hole. And then he climbs out of the hole and he walks over and again is standing under the tree. Okay? So we've got him back at the tree. So then they ask the questions. What was the difference between his starting elevation and his ending elevation? Well, he started and ended in the same spot. So that means that his difference between his starting and ending elevation is a 0. He didn't change elevation from where he started to where he ended. Now he changed as he went up to the house and down to the hole and back up, but from where he started and ended, there was no change. How far did he have to climb to get out of the hole? He had to climb up 8 feet. It says since vertical distance in a gravitational field are conceptually the same as voltage differences in an electric field, his voltage law is the exact same concept as what's demonstrated in this problem. Okay? So looking at his voltage law, at any instant, the algebraic sum of the voltage changes, increases, or decreases in any closed path in an electric circuit, and it must be 0. So at any instance, the algebraic sum of the voltage changes. So the increases or the decreases in your electric circuit, they're always going to have to add up to 0. Okay, so they give us a picture. Here it is. And for any closed path, so we've got a closed path here on our picture. And we know that the sum of the voltage changes must equal 0. And so it says an excellent way to do this is to go around the circuit and record the first sign we go to. So they put a little flag here. And then they go around and they just sum them. So this would be a positive 4. This isn't the right picture, guys. Hold on. Where did my picture go? All right, now we have the right picture. I'm sorry. So they put a starting point at this little flag here. And so as we go around, we're going to go this way, clockwise. We hit a negative 12, so that'd be a negative 12. And then we keep going and we hit a positive 4. And then we hit a positive 2. And then we keep going, we hit a negative 3. And then if we keep going, we hit a positive V sub 4. And all of those must equal 0. So if you add all of those up and then solve for V sub 4, you're going to get 9 volts. And so that'd be your V sub 4. So that's how you would use his voltage law. So we're going to look at an example. We have the picture, and they want us to find V sub CA. So what that means, this V sub CA here, means the voltage at C with respect to A. So A is the reference point, and so we're going to start at A. So we're going to start right here, and then we can go clockwise or counterclockwise. They usually go clockwise, so that's what we're going to do. We're going to go around this way. And so we hit a negative 15. And then if you keep going, you hit a positive 6. And then if you keep going around, you hit a positive 3. Oh wait, there's C right there. We don't have to go to the 3. To go to C, you get a negative 9. And so that's if you go from A to C. They wanted us to do from C to A. So if we went the other direction, if we went from C to A, we would get a positive 9. So VCA is going to be a positive 9 volts. And so that would be your answer. You start at C, and then you go to A. Okay, we've got one more example. All right, so looking at this last example, in the circuit shown, we want to find V sub DB and V sub AC. So we're going to go from D to B. So we're going to start here, and to get to B, all right, so we are going to go this direction from D to B. And so if we go this direction, we're going to get a -6. And then if we keep going around, we're going to have a +15. So we have a -6 and then +15. And so that gives us a +9 volts. So for part A, you get a 9 volts. That is a positive. I'm going to do part B in another color to find V sub AC. All right, so we're going to go from A to C, and so we're going to go this direction. So we're going to hit a -4, and then as we keep going, we're going to hit a -6, and so our total would be a -10 volts, and so that would be your B value there. Okay, so your homework is going to be 1 through 20, and the curveball questions 1 through 5, so make sure that you do that tonight so that we can go over any questions that you have tomorrow.